Yes, so hello everyone. Hope you're all doing well. So we're that today you came for the math behind cybersecurity and cryptography. But before that starts, I see some new faces, I see some old faces, and I hope that you don't mind that I first introduce myself, right? So I'm Ahmed Maghri, computer science major and mathematics minor, and currently the president of the Mathematics Society. So what's the Math Society itself? The Math Society, we believe in three words: think, calculate, create. Why? Because we think abstractly, then we calculate to make our ideas precise, and finally we create stuff that weren't existing before. And then you may ask, how do we do that? So, we events, basically. So, but which events? For example, the talk of today itself is the fourth talk of the series, The Math Behind. We had, first of all, the math behind AI, machine learning, and neural networks. Then we had the math behind poker and game theory, which was made by Professor Kevan. And then we had the math behind Interstellar. Not only that, but we also have our undergrad seminar, where we talked about golf mechanics modeling, string theory, Dorn integration optimization, but also dark energy acceleration of universe, Benford's law, and dark square time methods. Then you may ask again, what's even the undergrad seminar? So to explain briefly, the undergraduate seminar is an opportunity for students who apply and get accepted to conduct a 3 weeks research supervised by us, where they prepare some research in some specific topic, and at the end, they prepare the talk and get their paper reviewed, either peer-reviewed or reviewed by a professor. Why am I mentioning it? Because we'll have an undergrad seminar in 3 weeks and a half. And today, we'll open the applications for the next undergrad seminar. So keep that in mind. But let's stop talking about past events. Let's see what are our future events. So next week we'll have the math behind chaos given by Professor Ivan Ovsenikov. Then the week after we'll have the math behind causal machine learning, and the week after we'll have the math behind the undergrad seminar, and finally the math behind finance, which will be in collaboration with the Society, and many more. So I want to let you know that today, Math Society will be hiring. For the next 4 days, you have the chance to apply to become a board member of the Math Society. If you're interested in tech, logistics, finance, or even marketing, design, I'm pretty sure you'll find your place there. So if you believe that you have the qualities that will make you be accepted into the board team, don't hesitate to apply. Moreover, I would have a disclaimer. Today's talk, even if I try to make it as much as I can beginner-friendly, will still require some, say, basic knowledge of linear algebra. And while still I'll try to explain as much as I can, it will maybe happen that maybe you lose the track, or that I do calculation maybe too fast. In that case, just wait for it, and at the end, I'm pretty sure you can ask any question that you want, and I'd be completely happy to answer any question that you'd have. But this would be a bit heavier than math behind AI or ML, for example. Yeah. So I leave these QR codes here for 3 to 4 minutes for the time for you to scan them, and right after we'll start the actual talk. Thank you very much. So, hello again. And or he who برقة. Indeed, or he who برقة. For a while, I was wondering how to start my talk. I was like, should I start with a hello everyone? But that seemed too classic. And the idea I used for AI with the planets thing didn't work again here. So I was wondering how should I start it, and I think that one of the most valuable words was خور هي برقة. So what's خور هي برقة? It's actually cryptography. Cryptography is a concern that we had since centuries. People were always wondering, how do we make our communication safe, Or if I want to tell someone a secret, how can I make sure that no one else will understand the secret that I just told him? And when I say centuries, I really mean centuries. What I just used here is what we call Jules Caesar's cipher. So what's Jules Caesar's cipher? I believe you pretty much know Jules Caesar, but if you don't know it, it's Jules Caesar. It was the man that transformed the Roman Republic to the Roman Empire. Jules Caesar invented this algorithm to be able to communicate with his soldiers without that adversary people during the wars understand him. And he was able to achieve that. How? Even if it seems pretty complicated, it's actually a very straightforward algorithm. But I'm pretty sure that you know that Jules Caesar was existing in 200 before Christ. So then you can conclude that it is indeed true that cryptography was actually a very, very old subject. So how did Caesar do that? He basically would take each letter and shift it by 3. What do we have before K? H, if we come back by 3 letters. Before H, E, before O, L, before R, E. And you can get through this process and you would get hello everyone. So indeed, hello everyone, hope you're all doing well. And today, I'll take you to the math behind cryptography. Some of you might have been here last year, and might have been in my last year talk, which I called the qubit and Shor's algorithm. And then you may ask, why did I not call it again the qubit and Shor's algorithm? And what's even the qubit and what's even Shor's algorithm, What is it serve for? And is it the only stuff I'm going to talk about today? Well, last year I had 20 minutes to talk, and today I have a bit more. And I didn't call the talk the qubit and Shor's algorithm for a reason. But let me answer to the first 2 questions first. Shor's algorithm is an algorithm that was created to be able to break RSA, our most commonly used cryptography method. And we need a quantum computer to run Shor's algorithm. In these 2 sentences that I just said, you pretty much already heard 3 words that would qualify by a bit scary. Cryptography, quantum computing, and RSA. So in order to make you able to enjoy your journey with me, I would have to first then give you some foundations about what's cryptography, number theory, and quantum computing. So let's start with cryptography. I've said this word I think 20 times now. But what's cryptography? So cryptography is defined as the study of mathematical techniques for securing communication and data against adversaries. And in cryptography, we deal mainly with 2 subjects, namely encryption and decryption. And encryption is defined as the process of transforming information in a way such that ideally only authorized parties can decode. And RSA, as I said before, is only one of the most commonly used cryptography methods nowadays. So to explain how does RSA work, I think that the best way would just give you a very small example. I think you know these 2 people, Alice and Bob. You said that Alice and Bob are 2 friends. 2 lovely friends that meet each other every day, and they want to communicate to each other, but privately. And how are they going to achieve that? So let's say that Alice wants to tell Bob, hey, how are you doing? What Bob will do is that he will take 2 prime numbers, P and Q, and compute n such that n is equal to P times Q, what we call a semi-prime number, a number made by the product of 2 prime numbers. Then he will calculate the tangent function of n, then he will calculate E such that GCD of n tangent function of n is equal to 1. Then he will take D such that ED times is equal to 1 with 0 tangent function of n, and his private key would be ND, and public key would be NE. And now I lost 20% of people here. So to explain what's the torsion fraction of n, the torsion fraction of n is basically the number of integers that's more than n and that does not divide n. For example, if we take torsions of 6, what are the numbers that could possibly divide 6? 1, 2, 3, 4, 5, and 6 itself. However, 2 divides 6, 3 divides 6, and 6 divides 6. So we only have 1, 4, and 5 that do not divide 6. In that case, we say the torsion of 6 is equal to 3. What's GCD? GCD stands for greatest common divisor. So when you have two numbers, you check their possible dividers. For example, let's say 15 and 20. 15 dividers are 5 and 3, 20 are 5 and 4. The greatest common divisor they have between them is 5. And finally, modulo just means that we take the remainder. For example, when you have 5 modulo 3, you would check 5 divided by 3 gives a remainder of 2. And then we would say that 5 is equal to 2 modulo 3. Then you may ask what's this equality with three lines? It's what we call congruence. And that's a relation that qualifies in a better manner modulo. But for the sake of the presentation, I will, from now on, just watch an equality. Not because it's hard to write modules every time on the PowerPoint. So that's basically it. That's what Bob did from his side. So now, how is Alice going to send her text to Bob? So first of all, Alice will convert, hey, how are you doing, to a number. And that should be doable. You know, you can either use ASCII codes or you can use HEF8. There are many encodings, and at the end of the day, anything on a computer is at the end just some numbers, right? So she will have this number m, and then she will compute m to the power of d, or to the power of e, mod n. Again, recall that Bob published n and e, meaning that anyone in this whole world can know what's n and e. However, no one knows what's n and d. So Alice will send C to Bob. Bob will receive C, and then will compute C to the power of D, which will be equal to M. Why is that? Because M is equal to M to the power of ED mod N, following how we set it E and D. Then you may ask yourself, is that even secure? Maybe not, maybe yes. So let's say that we have a third person called Evil Man. Evil Man, as you can see in the name, is the one evil, right? Let's say that he was able to intercept C, the ciphertext. Ciphertext is a text that got encrypted. So he was able to intercept C. Would he be able to decrypt it? The answer is obviously no. Why? Because he doesn't know D. In order to decrypt C, he must know D to compute C to the power of D. And to know D, you need to know torsion fraction of n, because we computed D as ED is equal to 1 modulo torsion of n. And to know torsion of n, you need to know P and Q. Why? Let's try to calculate torsion fraction of n. Torsion fraction of n, which is again equal to PQ, is just the total number of possible dividers minus the multiples of P, because the multiples of P are the only ones that can possibly divide PQ, minus the multiples of Q, because again they're the only ones that can possibly divide PQ, plus double counted multiples. In case we have a common multiple between P and Q that will be removed more than once, we'd add it again. So, what's the total number? PQ, very obvious. How many multiples from P to PQ can divide PQ? We have 1P, 2P, 3P, 4P, all the way up to QP. So we have Q multiples. In the same fashion, how many multiples of Q do we have that can divide P? We have 1Q, 2Q, 3Q, all the way up to PQ. So we have P multiples. Notice that we removed PQ twice, because we considered that PQ is a multiple of P and Q. So then we have to add 1, because we double counted it. Then you can factor out here, and you get P factor of Q minus 1 factor of Q minus 1, and you can factor out and you get P minus 1 factor of Q minus 1. So in order to compute the torsion fraction of n, you need to know P and Q. But then you might ask me, okay, Ahmed, but if Bob chose, I don't know, let's say 13 and 11, and then n would be equal to 143. Even if it would take me some time, if I get 143, I would be able at some point to know that 143 factorials in 13 and 11. And let's say that I even did know what's 13 and 11, we can easily think that we can do, for example, for loop that checks all the numbers from 1 to 143, and it checks if it divides 143 or not. And we tell you, yes, you're right. However, when we execute RSA, we usually take numbers that are at least 300 digits long. Guys, 300 digits. Let's think about it. And when we take their product, you get a semi-prime number that is 600 digits long. So go try to make a for loop or go try to factor it out now. And that's indeed what RSA relies on. it relies on the fact that the time needed to factorize a big semi-prime number is really long enough to discourage anyone to try to find them. Remember this for later. Now, let's move to the second part, quantum computing. So, a lot of people hold that quantum computing involves states that are in 0 and 1 in the same time, or that quantum computers are usually more powerful than classical computers, which is true and wrong. A lot of people have a lot of misconceptions about what's actually quantum computing. So let's try to make it rigorous. So let's say they have a quantum state X. X is described by two amplitudes that we call A and B. What does A and B represent? We say that A represents the probability of measuring 1, and B represents the probability of measuring, A squared represents the probability of measuring 0, and B squared represents the probability of measuring 1. And you can imagine that we can write it in some vector notation. The vector with entries A and B, where the first entry would represent what's the probability of measuring 0, the second one represents what's the probability of measuring 1. And you can even imagine you can create a vector space where the bases would be 0 and 1. Then you'd get a basis with 0 and 1, and your vector would be lying in the unit circle. Why the unit circle? Because since A squared and B squared are probabilities, then their sum must be equal to 1 by root of probability. So A squared plus B squared must be equal to 1, which means that the vector would be a unit vector. And that's a state that was made by 1 qubit. If you had 2 qubits, we would have 4 possible states: 0, 0, 0, 0, 0, 1, 1, 0, and 1, 1. Then we would get, again, 4 probabilities: A, B, C, D, so A squared, B squared, C squared, D squared. And then we could even transform our 2D vector into a 4D vector, A, B, C, D. And then we could create a vector space with 4 dimensions. We can draw a vector space with 4 dimensions, guys. But you can pretty much imagine that we have some vector space with 4 dimensions where each axis represents one of the possible quantum states or normal states. So let's take an example to actually get it. Let's say that we have y that's equal to 1 half 0, 0, 1 half 0, 1, 1 half 1, 0, 1 half 1, 1, which will be represented in the column vector 1 half, 1 half, 1 half, 1 half. This means that we have equal probability of measuring each of our states. 1/4 probability. 1/4 plus 1/4 plus 1/4 plus 1/4 is equal to 1. And that's the key difference between classical computing and quantum computing. When we talk about what is read versus what is described. While in classical computing, in a bit, what is described is either a 0 or 1, and what is read is either a 0 or 1. In quantum computing, what is described is the probability of measuring 0 or 1. And what is read is then a 0 or 1. And in the same manner as in classical computing, we have some gates like the OR gate, the AND gate, or the NAND gate, and we could take these gates and bring them together to make more powerful stuff, RAM, multiplexers, or anything. In the same manner, we have also quantum gates. So let's take an example. A very famous quantum gate is what we call the poly-X gate. The poly-X gate is defined as follows. When you apply poly-X gate on 0, we get 1. When you apply poly-X gate on 1, we get 0. So it's basically kind of the NOT gate of quantum computing. So let's try to see the actual matrix of the poly-X gate. So the matrix of the poly-X gate is defined as 0, 1, 1, 0. And indeed, if you apply it on our two basis vectors, 1, 0, and 0, 1, you can do the computation yourself, and you will see that the coordinates get flipped. But then, you may ask yourself, okay, I know theoretically what's quantum computing, but how do we create a quantum computer, you know? In classical computing, we used to represent a bit by the presence or the absence of electricity. When it's off, we say that it represents 0. When the light is on, we say that it represents 1. However, we cannot use this exact same system to represent quantum computing. Why? Because there's no electricity, a bit absent or a bit present, which wouldn't make much sense. So we had to find another system that would be able to describe quantum computing. And physicians here would know that we use what we call the spin of an electron. An electron could be pointing down, which then would represent the 0 state. Could be pointing up, which then represents the 1 state. But could also be pointing somewhere in between, which would then represent a state between 0 and 1. And when we measure this electron, it either collapses to 0 or 1, with respect to some probability. And that's basically it. That's all what you need to know about quantum computing. And now, let's actually start talking about Shor's algorithm. So recall what I said before. we said that the time needed to factor out a semi-prime number is really long enough to discourage anyone to try to find them. If we are somehow able to break this axiom, by definition, we would be able to break RSA itself. And that's exactly the goal of Shor's algorithm. The point of Shor's algorithm is that given a semi-prime number n, find two prime numbers p1 and p2 such that their product is equal to n. Usually, in our classical computers, the most efficient algorithm to do such a thing is to guess randomly. You guess a number g, and you hope that maybe g divides n or shares some factors with n. The idea behind Shor's algorithm is that given this g, we want to transform it into what we call kind of a better guess. And that would be the first step of Shor's algorithm. Pick a number g such that g is between 1 and n. Then, to continue, we need to use a theorem. The theorem says that for any two whole numbers a and b that are co-prime means that the greatest common divisor with them is equal to 1, there exists a power r in n and a multiple of m such that h power of r is equal to m times b plus 1. Equivalently, h power of r is congruent to 1 modulo b. To make it simple, let's take an example. Let's say that we had a is equal to 2 and that b was equal to 5. If I take 2 to the power of 1, I get 2 modulo 5. 2 to the power of 2, 4 modulo 5. 2 to the power of 3, 8 modulo 5. 8 is bigger than 5, so we can reduce it. 8 divided by 5 gives a remainder of 3. 2 to the power of 4, 16 modulo 5. 16 bigger than 5, reduce it, 1. Notice that we found what we were searching for. We found a power, r, such that 2 to the power of some r would be congruent to 1 modulo 5. And thus, this would be the next step. So let's assume that we found our r. We found the r such that g to the power of r would be congruent to 1 modulo n, where recall again that g is our random guess and n is the number that we are trying to factor out. Then bring the 1 to the left-hand side, and then we can use our famous identity a plus b times a minus b is equal to a squared minus b squared to factor out g to the power r minus 1 to g to the power r half minus 1 times g to the power of r half plus 1 is equal to 0. Notice that we didn't find two numbers that divide n, but we found two numbers that divide a multiple of n. And it's actually pretty good. Why? Because we have something that is called Euclid's algorithm. I'm not going to explain how this Euclid's algorithm actually works, but what's important is that when you input a and b to Euclid's algorithm, the output is the GCD of a and b. Greatest common divisor again. So if you input in the Euclid's algorithm p1 prime and n, we would get either p1 or p2. Why? Because the only dividers of n are p1 and p2. Let's assume it was p1 or p2. Let's assume it was p1. Then you'd calculate n over p1, and you would get p2. And it would be the end of our algorithm. We were able to find p1 and p2 such that these two numbers, the product is equal to n. Or maybe not. Why? Remember that I gave you a whole lecture about quantum computing. And I didn't mention quantum computers at any point here. So why did I even mention what's quantum computing, you know? Where could have been quantum hidden in Shor's algorithm? Let's recall Shor's algorithm main steps. 1, make a random guess g such that g is more than n, that shares no factors with n. Second, find r such that g to the power of r is equal to mn plus 1. Third, if r is even, calculate g to the power of r half plus 1 and g to the power of r half minus 1. And if r is odd, go back to step 1. And fourth, use Euclid's algorithm to find the greatest common divisor. Where could have been quantum hidden here? It was actually hidden in the second step. How are we going to find r? I did mention this, right? And if I'm just going to guess randomly, that's completely inefficient. So we have to find a way to be able to extract r efficiently. And that's exactly the quantum subroutine of Shor's algorithm. To be able to run the quantum subroutine of Shor's algorithm, I would need two quantum registers. The first one would have a size of 2n with full zeros. The second one would have a size of n that is equal to 1. And the point of the quantum subroutine is that we're going to apply one gate into another to be able to somehow at the end extract our number r. And the first gate or the first transformation is what we call the Hahnemann transform. So Hahnemann transform, when we apply it on 1001, that's what we get. But as in our case, we're going to apply Hahnemann transform on our 0 state. So what matters for us is actually only this first line. So notice that when we apply Hahnemann transform on a 0 state, we get an equal probability of measuring 0 or 1. Because the probability of measuring 0 is 1 over square root of 2 square, which is 1/2, and 1 is also 1/2. What happens if we do it the same thing, but on a stage that made by more than 1 qubit. What if it was made by 2 qubits? We would get 1 over 1 half, 0, 0 plus 0, 1, 1, 0, 1, 1. What if it was made by 3 qubits? We would get then 1 over the square root of h times 0, 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1. Did you notice the pattern? Actually, whenever we apply Hadamard's transform on some zero state made by n qubits, we get all the possible states from 0 to 2 to the power of n minus 1 times the 1 over the square root of 2 to the power of n. Indeed, here we have the state made by 3 qubits. We got 1 over the square root of h of 2, 1 over the square root of 2 to the power of 3, which is h, and all the states from 0 to 7. Because 1, 1, 1 binary is equal to 2 to the power of 3 minus 1. This will be our first step. When we apply Hadamard's transform, that would be the current state of our resistor. Then we will try to express our whole quantum resistor into basically one full quantum system using what we call tensor product. Moreover, note that I can also simplify subtraction 0001 as only 1, just for notation purposes. Then you may ask what's a tensor product. For simplicity, let's just assume it's basically kind of a multiplication between quantum states. For example, I could use distributivity, and we will have A plus B times C is equal to AC plus BC. Notice that I even can stop writing the tensor product again, that's for simplicity. So what we have here is that we have a sum times one element. By distributivity, I can take this element and enter it in each term of the sum. So get the sum of all the x's times 1. Then, the next step would be to apply what we call the transform. The transform is not a famous transformation that was already defined before, but it's basically a transformation that Shor's defined in his algorithm. And how is it defined? When you input to U x tensor y, you get as output x tensor y tensor g to the power of x mod n, where again g is our random case that we guessed before, and n is the number that we're trying to factor out. So for example, if we apply U on a state 101 tensor 1, we would get 101 tensor y is equal to 1, so 1 disappears. G to the power of x is 101, which is 5 from binary, so g to the power 5 mod n. So if we apply U on our quantum state that we had before, we would get again the sum of x times g to the power of x mod n. And that's our current state. So I may have lost a lot of you here, and maybe you don't really get what's the state's shape right now. So let's try to take an easy example. Let's say that we have x that was going from 0 to 7, so a state made by 3 qubits, n was equal to 26, so n is the number that we're trying to factor out, and g is equal to 3. If I expand the sum, I get 1 over the square root of h, 1 over the square root of 2 to the power of 3, times 0, 0, 0, all the way up to 1, 1, 1, times 3 to the power of 0, to the power of 1, to the power of 2, 3, 4, 5, 6, 7. Since it's modulo 26, I can simplify. Then I get 1, 3, 9, 1, 3, 9, 1, 3. Have you noticed the periodicity? Indeed, we see that the quantum state repeats each after 3 iterations. And 3 was the first power that gave us 1 mod 26. Which means that if we are able to extract the periodicity out of our quantum state, we would be able to extract the power of R that we're searching for. Unfortunately, we can't. But we have something very cool that we call the quantum Fourier transform. So I won't go into too much details how does that work, because then I would have to explain what's the Fourier transform, and then explain what's the quantum Fourier transform, and this would be the whole talk itself. So for the sake of understanding, let's assume it's a black box. And when I will enter my quantum state inside of the black box, I would get out of it the frequency. To be more precise, we don't get the frequency, but we get the frequencies times some number j. So recall, and I hope you remember from high school, that frequency is equal to 1 over the period. And what's the period? The period is number r that we're searching for. So that's it. We found not r, but it's g over r. Are we done? No. Because even if you get a number, let's say that we got 0.312, what's r? You can't. Indeed. So that's why we will use the last algorithm of Shor's algorithm that is called the continued fraction algorithm. How does that work? You take your number and you flip it. Then you express this new fraction and again you simplify it. You do the same process again, and you keep flipping and simplifying until you get 1 in the numerator. Straightforward. Then, using this fraction, each line of the fraction will give us some approximation. For example, if we look at the first line, we would get that r is equal to 3, because this element would be negligible. If you look at the second line, we would get that r is equal to 13, because this element would be negligible. And if we continue, we get that r is equal to 16, because now no element was negligible. Each of the lines give us some approximation of r. So which one to choose? We will choose this based on two conditions. First condition, r should be trivially less than n. And second condition, it should be an even number, because recall if it's not, then we can't compute r half, and then our old method doesn't work. And that's the end of the quantum subroutine and the official end of the algorithm. So now in front of you together, we were able to break RSA. Given a number n, I was able to decrypt and know what was the initial factors P1 and P2. I said at the beginning that RSA is our most commonly used cryptography algorithm. So a very good question that I think you should ask yourself. Are we cooked? Since we already know, since anyone can decrypt RSA and anyone can be able to decrypt, to extract what's the two factors of a semi-prime number n, why are we even using RSA yet? Why are we still using it? And is there no method that we can use instead of RSA? Gladly, no, we have another solution. Cryptography always relied on finding some hard mathematical problems, and based on this mathematical problem, we try to create some encryption system. And our new hope is not coming from number theory, not from geometry, but both. You know numbers, you know geometry, so let's talk about the geometry of numbers. So in geometry of numbers, we deal with one main object that we call a lattice. So what's a lattice? We call L a lattice if L is a linear combination of vectors v1 till vd. So that v1 till vd is the basis of r to the power of d. You may still not get what's actually a lattice, and indeed someone very recently told me that reading definitions is a skill itself. So let's try to extract what does the definition mean. So first we need the basis. Let's say that we have a very classical basis, an orthonormal basis, right? Then we take linear combinations of this basis. For example, you could take 2 arrows red and 1 blue, and you get your first point, 2, 1. Or you could get, for example, 2 blue arrows and 1 red one, and you'd get 1, 2. And if you repeat this process again and again infinitely many times, you get your full lattice. And that's basically a lattice. Notice that the lattice could be completely described only by the basis. I do not need to know all of the points. I only need to know the basis elements. That was an orthonormal basis. But it could have even a more skewed basis, you know? Let's say that we have such a basis. Again, it would be the same thing. You could take, for example, 4 points, then again take some linear combinations, and repeat the process again and again and again until you get your full lattice. So what's the mathematical problem that's going to talk about now? Let's say that we had an even more skewed lattice with such a basis, for example. Now I'm going to ask you, what's the closest vector that we can create to the origin? Else than the origin, of course. You could say, if I take maybe 1 blue and 1 opposite of red, I could get the closest vector. Maybe, maybe not. Now I can come up and tell you that if we take 3 blues, 4 reds, 1 blue, 2 reds, 1 blue, and 1 red, we get a closer vector to the origin. That's what we call the shortest vector problem. It is that given some basis of some lattice, find the closest vector to the origin. Which is itself a hard problem, but you can even make it harder. From the shortest vector problem, we can move to what we call the closest vector problem. It's similar but different. Instead of talking about what's the closest vector to the origin, we talk about what's the closest vector to any random point on the lattice. And then you have to guess what's the closest vector to that green point. And maybe it's pretty hard. Even right now, you could see that I tried to find some linear combination, and I still need to add so many vectors to get close to the green point. And this doesn't guarantee that's the closest one. Maybe if I search from this side, I would get something closer. And based on this, we will try to create our encryption system. So the encryption system that is based on lattice-based cryptography is what we call the learning with errors problem. So what's the learning with errors? It is stated as follows. Take A being a matrix with n rows and m columns with uniform entries from over ZQ. What I'm talking about here now is search LWE. LWE, learning with errors. Because LWE itself is pretty much a mix of two subproblems. Search LWE and decision LWE. What this slide states is that we have a matrix with, for example, let's say in our case, 3 columns and 3 rows. And what does ZQ mean? This means all numbers over modulo Q. For example, in these cases, we have modulo 5. Any number would be reduced with respect to modulo 5. 7 would become 2, 10 would become 0, 6 would become 1, and so on. Then we need to consider more elements. Then it says that let S be a vector of length n with entries again from ZQ. And let E be a vector of length m with entries from some distribution x. Some distribution x that we don't know about, but some distribution x. We compute the following: A transpose times A plus A transpose is equal to B transposed. Notice that if we transpose the whole equality, these two flip and we get A transpose times S plus E is equal to B. This may seem easier, but this is more convenient to write, and you will see why later. The question that we ask itself then is find S. Given A and B, would you be able to find S? Notice that this is actually very close to something that we know from linear algebra. For example, we want to solve problem in the state, so matrix times S should be equal to B. That's a very straightforward linear equation, for example, that we can easily solve using, for example, Gaussian elimination. However, the big difference between an easy linear algebra problem and LWE is that we add some error to the equation, which means that we don't have x prime and y prime, but we have x prime plus E1 and y prime plus E2. And the point is that I'm not expecting you to extract the solution of this system, but I want you to extract the solution to the original S. Again, you're not given what's the error, you're just given the whole number, total number. And then even if you take, for example, with bigger matrices like 100 by 100, can you imagine as if you had 100 lines? Would 100 lines cross in one unique point randomly? Most likely not. And researchers were able to prove one big statement about search WE, which is for all NUPPT, adversary PR, adversary ABQS is equal to nickel N. The first time I read this, I was like, wow, what does that mean? It's actually very easy to read. Just check it slowly. First, we say that for all non-uniform probabilistic polynomial time, NUPPT, which means that any non-uniform probabilistic polynomial time, it's in the name. Then, for all adversary algorithms, an adversary algorithm is an algorithm that is trying to decrypt our text or to solve our problem. The probability that our adversary algorithm, given A, B, Q, to find S is equal to some negligible function n. Meaning that the probability of any adversary algorithm to find S is extremely low. What's a negligible function n? We describe a negligible function n as a function that is always smaller than 1 over any possible polynomial. So we could guess that it's actually extremely small. However, the problem with this statement is that it doesn't guarantee that we can't find any information about some parts of S. It is only speaking about finding all of S. It doesn't guarantee that someone cannot find some entries of S. It just guarantees that someone cannot find all the entries of S. And you can imagine that in cryptography, we don't want anyone to find some parts of our text. We want them to not find anything. Moreover, modern cryptography requires indistinguishability. What I mean by that is that, for example, if you're given a ciphertext and its possible origins M0 and M1, one should not be able to tell if it's M0 or M1 that is encrypted. So I'm giving you M0 and M1 and the ciphertext, and I'm telling you, okay, guess if this ciphertext was encrypted from M0 or M1, should not be able to say, okay, from 0 M for M1. And that's what brings us to the second part of LWE, what we call decision LWE. We have the exact same setup, the same instances and the same computation. The difference is in the question that we ask ourselves. We don't care about finding S this time. The question that we ask ourselves is, if given B, can we know whether is it just a random vector B or an actual vector that was created out of an LWE computation? Meaning that if I input to the LWE B it should output random if B was actually just a random vector, and LWE if B was actually extracted from some LWE computation. This itself is very close to LWE, but at the same time very different. Because fundamentally, in SLWE, we're solving a computational problem. We're trying to find what's S. While DLWE is a decision problem. We're trying to answer to a question by like yes or no, this or that. And people were able to prove two main properties about DLWE. First, DLWE is as strong as SWE. You will know later why I'm using this statement. Second, the probability of an adversarial algorithm of finding if B is equal to LWE minus 1/2 is negligible. Meaning that the probability of measuring of an adversarial algorithm to find whether B is uniform or is a random vector or actually a vector that's coming from LWE is very close to 1/2, which means that so any adversarial algorithm cannot do better than just randomly guessing. No adversarial algorithm can do better just taking a coin flip and hoping that it tells whether it's LWE or just random. And based on that, we will build our encryption system. So let's call again our old friends, Alice and Bob. Let's say that again, Alice and Bob are two very lovely friends that want to communicate privately. For the sake of the explanation, we're not going to talk about sending a whole text, but we will talk about sending a message M that is equal to either 0 or 1 bit. And you can guess that if I'm able to send a 0 or 1, I should be able to send any text. Because at the end of the day, anything is a string of 0 and 1s. So how are we going to do this? Bob will choose S and A both randomly from Z to the power of n mod Q. Which means that S and A are both some vectors with entries from modulo Q. Then E would be taken with respect to some distribution X. Then Alice would generate the following vector. A, then S transpose A plus E plus M times Q over 2 mod Q. Well, recall again that M is a text that we want to send, 0 or 1. Why she's generating such a vector, you will see soon why. However, she sends this vector to Bob. Bob receives a vector AB. He doesn't know what's exactly here. Just sees 2 entries. Then Bob computes B minus S transposed A. Why? Recall that B is equal to this thing, S transposed A plus E plus M times Q over 2. Which is equal to say that if we take this thing to the left-hand side, B minus S transposed A is equal to E plus MQ over 2 mod Q. Why is it important? For the algorithm to work, we would require one more condition. We would require that E would belong to minus Q over 4, Q over 4. And this with some overwhelming probability. Why? Because if you have this, then since E is belonging to Q over 4 minus Q over 4, then if M is equal to 0, E plus M times Q over 2, which is equal to this. Recall again that B minus the transpose of S times A is equal to this expression, would be equal to E itself, because M would be equal to 0, and this will disappear. Which means that this would be in the interval minus Q over 4, Q over 4. And if M was equal to 1, then we would get E plus Q over 2, which would mean that the text is in the interval Q over 4, 3Q over 4. And that's our decryption method. Basically, we decrypt S given A and B. We say that it's equal to 0 if B plus S transpose A is belonging in this interval. And that it's equal to 1 if it's belonging in the other interval. But is that even secure? How are we going to prove it? And when it is secure, what's even secure? In cryptography, we say that something is secure when we cannot distinguish by, for example, we cannot distinguish if the ciphertext was coming from 0 or 1. So let's try to prove it. So let's start from the left-hand side. The decryption of S0, we know that's equal to A plus S transpose A plus E mod Q. Recall that the element M times Q over 2 disappeared because M is equal to 0 in our case. Then, using the property of DLWE, we know that this is indistinguishable between this and just a random vector B, taken from some uniform distribution. Then we can add some constant, Q over 2, because the constant of set doesn't change the fact that B plus Q over 2 is still something random and something uniform. Then substitute back what was B equal to S transpose A plus E plus Q over 2 mod Q, again using DLWE. And finally, what's this? That's the encryption of 1, because here M was equal to 1 and Q over 2 was still present. So that's it. We were able to prove that we cannot distinguish whether we encrypted 0 or we encrypted 1. In that perspective, again, there's still one big issue. The problem is that Alice knows too much. When Alice wanted to send something to Bob, she had to compute the following vector. And to compute this following vector, she needed to know S, A, E, M, and Q. And that's what we call a private key system. Because here we assume that Bob before was able to send all of this to Alice without, with consider that like no one was able to intercept this. Because if someone is able to know all of this, then he will be able to also decrypt the text. That was, for example, the advantage that we had with RSA. RSA had a public key and a private key. And anyone using anyone's public key can send him a text. And he doesn't need to know the private key to send him the text. While the only person that is able to decrypt the text is the one that has the private key. So let's try to create a public key system in the same manner as we did, for example, with RSA. How are we going to do this? So again, let's say that I just want to send Bob 0 or 1. So we have the same S, E, and Q. And Bob will publish the following vector, A and B transposed, such that B transposed is equal to S transposed A plus E transposed mod Q. And this time we don't have one scalar A, but you have a matrix A. So Bob's public key is A, B, and Q. And Bob's private key is S and E. Meaning that anyone who want to communicate with Bob can be able to access and know what's A, what's B, and what's Q. But they cannot be able to access what's S and E. So in this case, if Alice wants to send something to Bob, the first thing she will do is that she will choose a random binary vector 0, 1 to the power of M. So a vector such that its entries are either zeros or ones. Then she will compute U such that U is equal to A times R. R is the vector she just chose, and A was sent in the public key. Then she will compute U prime so that U prime is equal to B transposed times R plus M times Q over 2. M is a text that you want to send to Bob. Q and B were both also in the public key. So she sends this to Bob. And the ciphertext is U and U prime. Then Bob computes, so Bob receives U and U prime and computes U prime minus S transposed U mod Q. Why is he doing that? Well, give me 1 minute to explain you what the computation is equal to. So what Bob had at the beginning was B, that's equal to S transpose A plus E mod Q, and what Bob computed is U prime minus S transpose U. What Alice had was this binary R in 0, 1 to the power of M, U that's equal to AR, and U prime is equal to B transpose R plus M times Q over 2. Replace B, but how Bob did compute it? So we get S transpose A plus E transpose R plus M Q plus M times Q over 2 mod Q. Using distributivity, we can separate these parentheses and get S transpose times AR plus E transpose times R plus M times Q over 2 mod Q. A over R is the U that we had before. So we get S transpose U plus E transpose R plus M times Q over 2 mod Q, since U is equal to AR. So therefore, we have U prime is equal to this whole expression. U prime is equal to S transpose U plus E transposed times R plus M times Q over 2. Notice that U prime is a scalar because we have a row vectors and a column vector, row vectors and a column vector, and some scalars here. So U prime minus minus S transpose U, we take this element to the left hand side, is equal to E transpose T R plus M times Q over 2. So that's what Bob computed. He has the value of this element. Notice that it's actually very similar to what we had before. Before we just had E plus M times Q over 2. So we would like to create a system which is very close. Depending on some interval, we would guess whether it's 0 or 1. So in order to be able to do that, we'd need such a thing, for example. At the end of the day, we want to be able to do something like that. That, for example, if M is equal to 0, you want this whole thing to be in Q minus Q over 4 times Q over 4, plus Q over 4 to Q over 4. And if m is equal to 1, we want this whole thing to be q over 4 to 3q over 4. To achieve this, we must establish one more condition, that the first norm of E should be smaller than q over 4. The first norm is the sum of the coordinates of E. Why is that? Because E gets multiplied by R. So R can either have 0 entries or 1 entries. And we want E to achieve such a thing, we want E to be in the interval minus q over 4, q over 4. So if we have all the entries of E that are minus q over 4 to q over 4, and if we know that its sum is always less than q over 4, then let's say in the worst case where R's entries would be full of 1s, then E transpose times R will just be equal to the sum of the entries of E transpose, which then should be normally smaller than q over 4. And this would give us our decryption. So we would say that we decrypt U and U prime if you have our secret key as 0 if U prime is minus S transpose U is in this interval, and to 1 if this thing is in the interval q over 4, 3q over 4. And that's basically it. We were able to create some encryption system such that we had some very secure communication. I called this at the beginning lattice-based cryptography. Where are lattices? That's the question you should ask yourself. Let's recall what LWE and how does it actually work. LWE is basically something like that. So H transpose S plus E is equal to B. Same question that we had before. But when we talk about some normal system of linear equations, what's actually solving a system of linear equations? For example, let's say that we had some basis vector, and we have this vector. Then we apply our matrix, and our space gets shifted, corresponding to what was the matrix. And then we ask ourselves, we have this vector, we have the transformation matrix. What was the matrix that when transformed is equal to the original vector? So we're trying to find this vector, then when it's transformed, outputs for us this new vector. That's linear algebra. That's not what's LWE. LWE is a bit harder. Instead of asking what's the vector that transforms to this, it asks what's the vector that transforms to the closest vector to the green one. Closest vector problem. Why is LWE strong? The proof that explains why is LWE strong is because we prove that SVP is a strong problem itself. And that's why we call LWE lattice-based cryptography. Now, you may have a lot of questions in your mind. So I said at the beginning that even after I showed Shor's algorithm, that we're able to break RSA. And still, I said that RSA is still commonly used nowadays. Well, I lied a bit. I also said that Shor's algorithm is a quantum computer to run. And we don't have a quantum computer. Currently, Shor's algorithm needs 20 million physical qubits to run. And currently, the main actor is IBM. And IBM is aiming for 4,000 physical qubits in 2026, which is extremely far for our 20 million target. Right? But then you may ask, okay, if I don't have a quantum computer now, why are we even caring about finding post-quantum algorithms? Well, for two main reasons. First reason is that some nations, for example, apply the principle of harvest now, decrypt later. What does that mean? Is that a lot of nations are for now collecting data, collecting data, waiting for the day we have a quantum computer to be able to decrypt all the data they have collected for the past years. That's actually something very true. That actually happens in the world. So the earlier we have an algorithm that is resistant to quantum computing, the better. Because then we wouldn't mind if someone finds a quantum, is able to build a quantum computer later. Moreover, even for example, the European Union has established such in 2030, all communication organizations will be forced to use post-quantum algorithms for their encryption methods. So it is indeed a very huge problem. Because the day we'll be able to break RSA, our data won't be safe anymore. So the correct question to ask ourselves is not if we're able to break RSA, but when. This was the math behind cryptography and cybersecurity. Wait, sorry. Thank you very much. Any question?
Question.
Yeah, sure.
Can you explain again the difference between the LWE? I think there was like the search LWE.
Yeah, essentially. Okay, wait.
The second one, you're trying to guess if the Q that you input is
If the B is a random vector or something is actually coming from.
Change your base.
So that's LWE. Yeah. So the main difference between LWE and SWE is basically about this. Is that in SWE, instead of asking this whole question, the question that we ask is ourselves is not this, but to find S. That's basically it. In search LWE, we're trying to search what's the vector that satisfies this equation. Where in DLWE, we given the B, we try to know whether B was a randomly generated vector or a vector is coming from the combination of LWE.
And so if this vector is found, it means that the message is decrypted, right?
So in search LWE?
Yeah.
So search LWE, so that's the point. We didn't. So first of all, as I said before, we show that for adversarial algorithms to find S, the probability is extremely small. However, we didn't rely our encryption system on LWE because SWE doesn't guarantee that we cannot find all of S. That's why we moved to DLWE. And with DLWE, we base our encryption system on it. In that perspective, then our encryption system is independent from DLWE, from SLWE. Sorry. The only reason why I said like they are both as strong as each other because DLWE is as strong as SLWE, and SLWE's strongest is proved by the closest vector problem that I said at the end. Okay. Any other question?
You said it was a closed vector problem because when you're trying to go back, you're trying to find the original vector that gets mapped to the closest.
Exactly. Yeah.
To the point.
Yeah. Basically. Yes. Any other question? Yeah, but. Yeah. Then, if that's everything, yeah. Question? Okay. Then thank you very much for all coming here today, and see you soon then.
Professor.
So we are doing a video for the math club, and we want to ask you guys some questions, very easy questions. Does anybody want to be part of the video?
What type of questions? Sure.
It's just like
Math questions or like?
no, it's not. No, I'm not gonna give you no formula or anything. It's just more of your experience here. Like, did you like it? Did you not? Any improvements that we can do? Anything. Okay. Okay.
Thank you for this. So you're exploring the topic and spread it to others.
I mean, yeah, that's basically it. Well, thank you also very much, Professor, for coming. Hope you liked it.
Yes, I like because everything is done behind. I mean, it's public and private keys. So I used this, but had no idea what.
Oh, actually.
what is behind.
Oh, okay. I'm glad then. But like I tried to basically do like a second version of my last year's talk, like where because last year's talk was I'd say a bit lot superficial, so I tried to get like deeper in it basically. But I don't know. It's not my main interest to be honest. Like currently I'm more leaning towards like AI and such stuff. But I mean, yeah, like I was like, let me learn about it, and I did talk about it. That's basically it. Hope it was good.
Did you record last week?
Thank you.
Oh, no worries. Thank you very much, Professor, for coming again.
Can we do this one? Sure. The other one? I don't even. Yeah, because there was some that looked more.
I had my
laid back.
iPad.
Okay.
But yeah, I think we should just.
Which one has better quality?
I think I don't know. I don't know which one are you.
I wouldn't mind whichever you guys.
Okay,
But
but we need to
whichever
take
looks
some
better.
pictures of you too, because when you were
Yeah,
talking,
whichever
all
looks
of them
better.
turned out like. Yeah. Okay.
How many questions would you want me to do?
Not many, because like the video will be long.
Okay.
Yeah.
Can we pause it for me to later like pull up there?
Ain't gonna lie, dude. Like what you said was a lot.
Thank you, man.
There was actually a lot to be honest, but like,
Okay, come
I
on.
was actually trying to keep up, to be honest.
I'm glad. I tried to make it not too hard, to make it still like, to some extent, beginner friendly. I did my best. I hope I achieved
Yeah,
something.
yeah, you did your best, bro. Just that the concepts, to be honest.
Yeah, indeed, it's very hard. But it's fine.
Wait, so what's up?
I mean, you had it with the. You had.
I did this today and I feel too much mass major.
Hey, bro, congrats. Awesome shit.
Thank you.
You bamboozled us, bro. This guy bamboozled us. He was like, I wasn't done with my previous talk, so I'm gonna.
Oh, yeah. That's actually true. Now I would be proud.
Oh my god, great stuff, eh? Great stuff.
Thanks, man. But I'm
Short
tired.
algorithm.
No, I slept like 4 hours today. I had to finish this. 3 hours, 4
You're
hours.
so smooth with the presentation, though. Like you're so
Yeah.
smooth. I
Like transitions.
yeah, the
I tried to work on it a lot.
Like they were like, so where are the lattices? Where are the lattices? We said it's a lattice-based encryption,
Yeah, and where are the lattices?
but no lattices were mentioned.
I wonder, do you guys like have lattice theory or something?
Yeah, never theory. Oh, yeah, that theory.
We did. Oh, we did.
Yeah, Professor Kevin, yeah.
That was like 2 weeks.
See you, man. Take care. Thank you very much for coming.
And I think in discrete math, there might be at some point some lattice.
Yeah, most likely. Graph theory and
Graph.
stuff.
Yeah.
Math majors don't take numerical methods.
No, they check stats and data analytics.
I mean, we did computational modeling where we do
Yeah.
basically numerical.
No, to be honest, like, I looked at both of them. Numerical model has more stuff first, but also numerical is like completely theoretical, while component is like completely practical. Like in numerical methods, we don't code at all. Like, he said, like first thing he said is like we won't code at all. Like everything will be like do it with your hand, you know.
Oh yeah, I'm glad I'm not taking that class, bro. But you know, like,
I'm only taking it because of masters. Otherwise, I wouldn't have taken.
because computational modeling, like, it's the same algorithm, same shit.
Yeah, indeed.
Or I mean, maybe not all of them, but like a couple of them.
You notice? Morocco.
Yeah, bro. Yeah, you gotta work. Yeah, of course.
Oh, Morocco.
Yeah.
But you actually do the program, you know, like.
Yeah.
Were you here for the Runga-Kutta talk?
Wait, sorry.
Runga-Kutta method.
No, I was not here, but
It's like a method to solve differential equation. I mean, you probably know it. You've heard of it.
I know it. I'm taking numerical methods now, but I know it.
I'm also taking. Are you taking numerical as well?
Yeah, I saw you.
Oh yeah, I'm taking this extra.
Yeah, I don't know.
Do you know Euler's method for differential equations?
I know it. I applied that.
Like the step method where you like kind of like take the small little gradient.
You thing? Yeah, I know.
This is like the OP version. And the in computational modeling where you kind of just use it. You actually solve a differential equation.
Yeah.
You graph it. You see the result. You know, which is
You're
nice.
also a math. You're a math major, right? Yeah.
So it's good to get our hands dirty
I
once in
don't
a
see
while.
differential equations very often, honestly. In my
Yeah, like I don't know.
I mean, yeah, fair. Like it's
CS major.
finite.
Yeah.
But I love differential equations.
I
Burning passion and love for differential
But I have-
equations. It's impressive.
I have developed the same passion as well since I have to bother with the dynamical systems.
Yeah, no, but like, are you gonna do like chaos theory, like bifurcation theory.
So, are you doing your thesis now as well?
Not started yet, but I already like managed the. I'm gonna do with Professor Ivan, and my topic is exact. I just like did a little bit of research on it, took some courses. I will do bifurcation theory, but not chaos theory because I think it's so scary. I just like looked at what's that Dragunov?
Wouldn't that be like a math major thesis?
No, actually, I'm gonna do the simulation.
Okay. Math major thesis.
You're gonna love this shit. No, I don't have my laptop. Oh my god. Because I've done some simulations of dynamical systems in Python. Let me show you my other videos.
Wow.
They're not very powerful, right? Because like I was just playing around.
What are you using for visualizations?
Pygame.
Oh, yeah, that makes sense.
So look, I was plotting the attractors. The attractors, and this is what.
bro,
This is so lovely.
you want to say something before I end the live?
This is like Kita map. But this is the attractor, but I was like actually simulating them. Wait, look at this shit. Look at them.
Oh,
This is beautiful.
oh, lovely.
Yeah. Yeah. And that's, I mean, this is me changing the parameters, so it's bifurcation, you know? It's like
yeah,
it's
that's
bifurcation.
good.
Like, this is a logistic map, and it will like create some weird patterns. And like, wait, like, let it move, and look at it. Like, it was crazy.
Oh shit.
It was crazy. It was crazy.
Oh, it
I
looks
was like,
beautiful,
like, I can send it to you because it's in my.
That's very cool.
Yeah, it's nice. It's in my GitHub, so like you can access it whenever. But I'll send it to you if you want.
Do you have my contacts?
Do you have my contacts?
Okay.
Okay, wait, no. Send me your just put your Insta.
If you write Prince, that's gonna appear. We are in